Hey guys, it's IBM. I'm still taking you through magnetic fields and electromagnetic induction. I think this is going to be part 28 of these episodes. These are past paper questions up to 2025. Question 84. Electrons enter a rectangular slice P, Q, R, S, F, E, F, G, H of a semiconductor material at right angles to the face PQFE as shown here. A uniform magnetic field of flux density B is directed into the slice at right angles to face PQRS. The electrons each have a charge minus Q and drift speed V in the slice. State the magnitude and direction of the force due to the magnetic field on each electron as it enters the slice. Of course, we know that the magnitude of the force on the charged particle in a magnetic field is given by BQV. So magnitude is force equals to BQV. Then direction. So the electrons are entering that direction. Therefore, we make the second finger of Fleming's left hand to point in the opposite direction. It's what I try to demonstrate with this hand here. The field is vertically downwards, so the first finger points downwards. When you try to make the second finger point in this direction, in the opposite direction to that of the electron, you notice that the thumb points to the left-hand side, which means that the electrons are going to be pushed towards this edge, this face here, using Fleming's left-hand rule. So the direction, that is from, we can say from P to Q, or from S to R, or from H to G, or from E to F, or we can say from the face PSHE towards QRGF. So direction we can say from, say P to Q, or from E to F, or from S, that S to R, or that is H, from H to G, or you can say from face PSHE towards QRGF. So the electrons are drifted towards the face that I've shaded here, using Fleming's left-hand rule. The force on the electrons causes a voltage VH to be established across the semiconductor slice given by the expression VH is equal to BI over NTQ. State the two faces between which the voltage VH is established. So because the electrons are drifted towards this end, the other end is going to be positive. Therefore, there's a potential difference between PSHE and QRGF. So this is going to be PSHE and QRGF. Use letters from the figure to identify distance T. Of course, T is the thickness of the slice, which can be QF or PE or RG or SH. So T is the thickness, so the answer here can be PE, or it can be QF, or it can be RG, or it can be SH. Aluminium has a density of 2.7 grams per centimeter. Assume that there is one free electron available to carry a charge per atom of aluminium. Show that the number of charge carriers per unit volume of aluminium in aluminium is 6.0 times 10 to the power of 28 per meter cubed. So we want to find N. So I'll use concepts of nuclear physics and maybe ideal gases. You and me know that number of moles equals to number of particles over Avogadro's number, which is mass over molar mass, which means that the number of particles is going to be equal to mass over molar mass times Avogadro's number. And of course, we know that mass can also be density times volume, where the density is 2.7 grams, which is the same as 2,700 kilograms per meters cubed. That is density. So it means this is going to be, the number of particles is going to be density times volume divided by the molar mass, then times Avogadro's number. And the number density, of course, I don't want to use this N for number of moles because N is going to be number density here in this part here. So the number density or the number of charged particles or number density or number of charge carriers per unit volume is going to be the number of particles divided by the volume, which is going to be equal to density times volume times Avogadro's number divided by the molar mass times the volume. Number density is number of particles per volume, so volume cancels out. When the volume cancels out, you remain with density, which is 2,700, then times Avogadro's number, which is 6.02, times 10 to the power of 23, divided by the molar mass, which is 20. Of course, the molar mass is the mass in grams. This is the molar mass, 27 grams, which is 27 times 10 to the power of minus 3. So the molar mass is 27 times 10 to the power of minus 3 to change it to kilograms. So when we check with our calculator, we have 27,000 times 6.02 exponent 23 divided by 27 exponent minus 3, that is 6.02 times 10 to the power of 28. So this is going to be 6.02 times 10 to the power of 28, which is approximately 6.0 times 10 to the power of 28. Okay. A sample of aluminium foil has a thickness of 0.09 millimeters. The current in the foil is 4.6 amperes. A uniform magnetic field of flux density 0.15 teslas acts at right angles to the foil. Use the value in Roman 1 to calculate the voltage VH that is generated. So voltage VH is going to be equal to B times I, because the formula is BI. So B is 0.15, the current is 4.6, divided by N. N is 6.0 times 10 to the power of 28 times the thickness, that is 0.09 times 10 to the power of minus 3, then times that is the thickness, then times charge 1.6 times 10 to the power of minus 19 coulombs. So we just press our calculator. 0.15 times 4.6 divided by 6 exponent 28 divide by 0.09 exponent minus 3 divide by 1.6 exponent minus 19. So that is 7.986 times 10 to the power of minus 7 volts, which is approximately 8.0 times 10 to the power of minus 7. Okay. A solenoid S has a small coil C placed near to one of its ends as shown in the figure. Okay, so that is the solenoid S and a small coil C placed in their vicinity. The coil C has a circular cross-section of diameter 3.6 times 10 to the power of minus 2, so the radius is 1.8 times 10 to the power of minus 2, and 63 turns of wire. The solenoid S produces a uniform magnetic field of flux density B in Tesla in the region of coil C, given by the expression B is 9.4 times 10 to the power of minus 4 times I. Where I is the current in ampere in the solenoid. The variation with T of the current I in solenoid S is shown by the figure. State two times at which there is no EMF induced in a coil C. Now, I want you to notice that the induced EMF is directly proportional to the rate of change of magnetic flux linkage, which is going to be directly proportional to the gradient, because a constant current produces a constant magnetic field, which means a rate of change of magnetic flux linkage will be 0. A changing current produces a changing magnetic field. So, it means that the induced EMF is directly proportional to the gradient of that graph. Where the gradient is 0, it means the induced EMF is 0. Where the gradient is maximum, the induced EMF is maximum. So from this curve here, we shall notice that the gradient is going to be maximum at this point here, maximum here, because the tangents are steeper in those points. So there is no EMF. The tangent at this point will be a horizontal line whose gradient is 0, horizontal line here whose gradient is 0, horizontal line here whose gradient is 0, horizontal line here whose gradient is 0. And wherever the gradient is 0, the rate of change of magnetic flux linkage is 0, which means the induced EMF is going to be 0. So time for which the EMF is 0, we have T1, we have T3, we have T5, and we have T7. You just choose only two values of time. Okay, then the induced EMF in coil C is a maximum, but with opposite polarities. So where the gradient is maximum, the induced EMF is maximum. But you notice that the gradient here is negative, the gradient here is negative, the gradient here is positive. So here at T2, the induced EMF is maximum, but has the same sign as the induced EMF at T6 and also maximum. However, T2 has opposite sign to T4 because here the gradient is negative, yet here the gradient is positive. So the values of time we are looking for which the EMF is maximum, but opposite signs are either you can choose T2 and T4, or you can choose T4 and T6. Okay. The alternating current in the solenoid S in B is replaced by a constant current of 5.0 amperes. Calculate the average EMF induced in a coil when the current in the solenoid is reversed in a time of 6.0 milliseconds. So if the current is reversed, means it leaves one maximum through 0 to another maximum. So this time here is for between two maxima. So the time from maximum to 0 is half of this. So the time should be half of. So since the current is reversed, time to reach maximum current in one direction from 0 is going to be half of that. And remember, the e.m.f is directly proportional to the rate of change of magnetic flux linkage. So the e.m.f is equal to N times change in flux divided by time, which is the same as NBA divided by T, or divided by delta T. The number of turns in the coil, I think it was 63. 63. It is 63. So that is 63 times the magnetic flux density. It was B equals to 9.0 times 10 to the power of minus 4 times I. So this is 9.4 times 10 to the power of minus 4 times the current, which is 5.0, then times the area of the coil, that is going to be pi r squared. So that is pi into 1.8 times 10 to the power of minus 2, but this is squared. Then divide this by the time. Remember, I said the time is 6.0 times 10 to the power of minus 3, but this time should be divided by 2, because it is the time from 1 maximum, say positive maximum, through 0 to negative maximum, if the current is reversed. Okay, so this is the same as multiplying this by 2. So this is going to be 63 times 9.4 exponent minus 4, then times 5 times pi, then times 1.8 exponent minus 2, but this should be squared, then divide by 6.0 exponent minus 3. I'll just multiply by 2. So that is 0.10. 0.10 volts. A horseshoe magnet is placed on a top pan balance. A rigid copper wire is fixed between the poles of the magnet as illustrated here. The wire is clamped at ends A and B. When a direct current is switched on, the reading on the balance is seen to decrease. Now, if the reading on the balance is to decrease, it means that the force on the magnet is upwards. That's why the reading is decreasing. If the force on the magnet is upwards, by Newton's third law, the force on the wire should be downwards. Set and explain the direction of the force acting on the wire. So a decrease in the balance reading, decrease in the balance reading implies that the force on the magnet is upwards. If it was downwards, the balance reading is supposed to increase. Decrease in the balance reading implies that the force on the magnet is upwards. I'm saying if it were downwards, the reading would increase. By Newton's third law, the force on the wire due to the magnet, the force acting on the wire must be equal but opposite to the force acting on the magnet. So the force on the wire, so the force acting on the wire is downwards. The current calculate the current, state and explain the direction of the current in the wire. Okay, now that we know that the force on the wire is downwards, the magnetic force on the wire is downwards, so the thumb should point downwards, and of course the field lines originate from north to south, so the field should be in that direction. I tried my level best to demonstrate this with my left hand, but it's not very perfect. I couldn't make it point exactly in that direction. So the field is in that direction. Make the first finger point in that direction and try to make the thumb point downwards. You will see that the second finger, which shows the direction of the current, will be in that direction there, which means that the current is going to be from A to B. So we shall say that since the force on the wire is downwards, by Fleming's left-hand rule, the current is from, did I say the current is from A to B? So making the force to be downwards, if you try to make the thumb to point downwards, and the first finger is that direction, the second finger is going to point the other way around. It is pointing that side. Try to use your left hand and see, sorry for that. So it is from B to A. So I will say that since the force on the wire is downwards, by Fleming's left-hand rule, the current is from B to A. Okay, so the current is from B to A. A direct current of 4.6 amperes in the wire causes the reading on the balance to change by 4.5 times 10 to the power of minus 3 newtons. So 4.6 DC causes the force to change by that. The direct current is now replaced by an alternating current of frequency 40 Hz. Frequency is 40 Hz, which helps us to find the period. On the axis of the figure 8.2, sketch a graph to show the change in balance reading of a time interval of 50 milliseconds. Okay, so I'm going to start with the period. So period is going to be 1 over frequency, which is 1 over 40. I think 1 over 40 is 0.025 seconds. Since this is in milliseconds, that is 25 milliseconds. So one cycle will be here. Another cycle should be here. This is 25. So if this is 25, half a cycle is going to be here. And this is 12 and a half. 1, 2, 3, 4, 5, 6. So a quarter a cycle is going to be somewhere here. Somewhere there. Then 3/4. Okay, let me first find the maximum change in force. So we know that force equals to B, and we know that the peak current is equal to the root of 2 times the I root mean square. So the peak current is going to be root mean square is 4.6 times root of 2. That is the peak current. So the peak force, F naught, is going to be equal to a constant times, of course, B and L are constants, so times 4.6 root of 2 divided by the initial force, which is 4.5 times 10 to the power of minus 3 divided by the same constant times 4.6, which means that find the peak force is going to be plus or minus 4.5 times 10 to the power of minus 3 root of 2, which is going to be equal to 4.5 root of 2, that is 6.4. So this is plus or minus 6.4 times 10 to the power of minus 3 newtons. And the scale on the vertical is 0.4. So 6.4 is one box. So that is going to be there. Of course, this is going to vary sinusoidally, just like the current. So this is going to be like this. It goes to 0. Then it goes to maximum at around this point here. Then back to 0. That is full cycle. Then another quarter will be at 1, 2, 3, 4, 5, 6, almost here, around there. Then it goes to 0 at, that is 25, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and a half. So it goes to 0 at this point here. Then it goes to maximum 1, 2, 3, 4, 5, 6. So it reaches maximum again at around 1, 2, 3, 4, 5, 6. I think it's around here. Then it goes back to 0. Okay. So the most important point is that it goes through 0 at 25 and so on and so forth. And also note that the peak is positive. It is positive 6.4 and negative 6.4. So that's where we expect us to have our peaks. We expect the peaks or the peak values to be at those points. And we also expect that one cycle should be in 25 milliseconds and two cycles that should be in 50 milliseconds. Okay, so I think that is the graph. A cross section through a current carrying solenoid is shown in the figure here. On the figure, draw field lines to represent the magnetic field inside the solenoid. So field lines to represent the magnetic field inside the solenoid. So I'm going to imagine, because the bottom circles are showing current out of the page and the top circles are showing current into the page. So I'm going to pick one pair and I'm going to draw a magnetic and an electric field line in these 2 points like this. So imagine I've chosen one field line, one electric field line. Here it is coming out of the page and there it is entering into the page. So it means if I was to put so many electric current lines showing the direction of current, there will be, the fingers are going to be folding upward. So imagine gripping your conductor in the right hand with the thumb pointing the direction or pointing towards the north. So the fingers are supposed to be folding upwards as shown in this, as illustrated here. because the current is coming out of the page here and is going into the page that side. So the fingers are supposed to be folding upwards as shown with this diagram here, and with the thumb points to the north, which makes this end north and this end south. Therefore, the magnetic field lines are going to be at the center. Of course, you draw a straight line with the ruler, and the lines terminate to the north, they originate from the south. And of course, I'll draw, you can't draw one field line, then I'll draw others. You can draw others. Okay, so the field lines are going to be like this. Remember, at the center, you draw a straight line. So that is the magnetic field pattern in there. So you don't make sure you draw at least 3 field lines. I've drawn 1, 2, 3, 4, 5. A coil of insulated wire is wound onto a soft iron core. The coil is connected in series with a battery, a switch, and an ammeter as shown here. Use laws of electromagnetic induction to explain why, when the switch is closed, the current increases gradually to its maximum value. When the switch is closed, the reading of the ammeter gradually increases to its maximum value. It gradually, instead of rapidly becoming maximum. Okay, so that is now Lenz's law. Use laws of electromagnetic induction to explain why, when the switch is closed. When the switch is closed, of course, by Faraday's law, there's a change in magnetic field from 0 to a certain value because the current is going to be flowing. And by Faraday's law, an e.m.f is going to be induced. But the induced e.m.f tends to oppose the change producing it. That is in accordance with Lenz's law. Therefore, this prevents the induced e.m.f prevents the battery e.m.f, thereby preventing the current from growing rapidly. So I will say increasing current in the coil causes increase in magnetic flux in the core. Because when you close the switch, there will be an increase in current in the coil, which causes an increase in the magnetic flux in the core. Increasing magnetic flux induces an e.m.f in the core. That is Faraday's law. The induced e.m.f opposes the growth of current in the coil. The induced e.m.f in the core opposes the growth of current in the coil. This is now Lenz's law. Remember, increasing the current in the coil causes an EMF to be induced in the core. Again, the induced EMF in the core opposes the current in the coil from growing or from increasing. And this forces it to increase gradually rather than rapidly. To increase gradually instead of rapidly. So that's why it grows gradually instead of rapidly. Lenz's law. If we close the switch, there's an increase in current in the coil, which by Faraday's law, it induces an EMF in the coil, in the core. The induced EMF in the core then opposes the growth of current in the coil, because remember, an EMF, the induced EMF is always such as to oppose the change producing it. The change producing EMF in the core is the increase in current in the coil. So the induced EMF is going to try and oppose the growth of the current in the coil, which is producing the EMF in the core. That is in accordance with Lenz's law. Okay, I think that is part 28. See you in part 29. Bye bye.